Hello everybody, my name is Hasbil Yadi, and today we're going to talk about a dynamic machine learning workflow for production optimization. Thank you for PetroLearn for the opportunity to present on this topic, and thank you for listening today. So the agenda for today is going to be pretty interesting. We're going to talk about what machine learning is, different types of machine learning, and also we're going to talk about different algorithms, and then we're going to show you a case study on how we can use machine learning in the oil and gas industry to optimize production performance of wells. So the first slide that I want to talk about is what is machine learning. So machine learning, so as you guys know, as the volume of data increases, human cognition is no longer capable to decipher important information by conventional techniques. So if I have a data set that has, let's just say, 10 wells, okay, and I'm trying to understand the impact of different completions design or different way of producing the well on production performance, I can look at 10 wells and I'm able to decipher, important information from the wells, like with 10 wells, as long as there's not much variability in the data set, right? But now, if I have 2,000 wells, 10,000 wells, or 500 wells, and I'm trying to decipher important information from the data, then it becomes very challenging. And in those cases, then I would have to use some type of a machine learning algorithm to decipher that information, to find those patterns, and that's what machine learning is. So and there are different terminologies that are being used interchangeably, and they're called AI, machine learning, data mining, and deep learning, and so on and so forth. So before we dive into that, I want to just clarify what each terminology is, okay? So first off, AI is the artificial intelligence, and it just means using machine intelligence as opposed to human or animal intelligence to decipher important information from the data. That's what AI is, right? So that's AI. Then machine learning is a subset of AI. So machine learning is unfortunately used interchangeably with AI, but it's not the same as AI. Machine learning is a subset of AI, and machine learning concentrates on performing a specific task. Okay, that's what machine learning is. So, for example, teaching someone how to play basketball is machine learning, but using someone to find the best basketball centers in the city is data mining. So again, the difference between machine learning and data mining is that one, you're trying to teach someone how to use, like how to play basketball, and the other one, you're trying to find the best, basketball centers in the city. And then finally, deep learning. We always hear about deep learning, and deep learning is basically an algorithm called artificial neural network with multiple layers. So examples of deep learning could be convolutional neural network, recurrent neural network, which is called RNN, and so on and so forth. So those are basically mean using an artificial neural network with multiple hidden layers. So now that we understand what the difference between machine learning, artificial intelligence, data mining, deep learning, let's talk about different types of machine learning. Well, first one is called a supervised supervised machine learning. And what that is basically means I have my input features and I have my output feature or features. So let's just assume that you're trying to understand the relationship between different completions parameters such as stage spacing, proppant per foot, water per foot, sand to water ratio, and so on and so forth. And you're trying to understand those metrics, their impact on production performance, such as EUR per 1,000 feet or cume per cume per thousand feet, or you can use any production metrics such as A root K or A square root of K per foot to kind of understand the impact of those parameters on production performance. So in this case, you have your input features, which are your stage spacing, cluster spacing, and so on and so forth. And you have your output feature, which is cume per foot, EUR per foot, or A root K per foot. So this is called a supervised machine learning model. So it just means that you have your data is labeled. You have, your EUR is your output, and in this case, since your EUR is a number, it is considered to be a regression model. And if instead of EUR you had let's just say true or false as your output feature, then that would be a classification problem. Or if you had yes or no, true or false, or you had good, bad, or just whatever that you can imagine, those would be classification problems, and you can have a supervised regression model, or you could have a supervised classification model. So that's basically supervised. So the best way to think about supervised learning is to think about, hey, I have my input features and I have my output feature or output features. You could have multiple outputs. You could have, you could be trying to predict cume per foot as a function of time. You could predict cume 30 per foot, cume 60 per foot, cume 90 per foot, and so on and so forth. So you could have a model that has multiple outputs, and in this case you have a multi-output supervised machine learning model. Okay. The next type is referred to as unsupervised. Now, when people say unsupervised, they're referring to that there is no target or output variable to predict or estimate on. In the supervised learning, you're training a model based on your inputs and your outputs or outputs. But in unsupervised, you have no target class. So you have, let's just say, a set of data, and you just want to cluster your data. If you want to, you can use different clustering techniques such as k-means clustering, hierarchical clustering, density-based type of clustering called db-scan. You can use a clustering technique, to cluster your data, and that is called unsupervised. So in that case, you have no target or an output variable. And then finally, the last type is called or the third most important type is called the reinforcement learning. And in that case, the machine trains itself on a continual basis. Now that you understand different types of machine learning algorithm, let's talk about some of the examples of what is considered a supervised, what is considered an unsupervised, and what type of algorithms are considered to be reinforcement learning. So supervised, you guys have probably heard these. We have artificial neural network called ANN. Support vector machine is a very powerful technique used for both classification and regression problems. You have k-nearest neighbor, another powerful technique that you can use for both classification and regression problem. Random forest is another very powerful technique that is used for both classification and regression problems. You have decision trees. You have extra trees, which is the extreme random forest called extra trees. You have gradient boost. You have adaptive gradient boost. You have linear regression, logistic regression. These are all different types of supervised machine learning algorithms, and there are many more. And then the second type, as we discussed, was the unsupervised, and you have examples would be k-means clustering. You have hierarchical clustering. You have density-based spatial clustering of applications with noise, which is called db-scanned. And then you have the a priori algorithm, which is another type of unsupervised learning. So in all of these techniques, you're pretty much clustering your data. And then the third type is called reinforcement learning, and you can you use Markov decision process, Q-learning, these are some of the examples of reinforcement learning. Now let's talk about let's talk about the process, the workflow. How do we build a machine learning model? You hear about machine learning and all these things a lot, but I want to break it down and kind of put it in layman terms, what we're trying to do here. And the process is actually not too complicated once you understand what you're trying to do. So step one, as you probably read or seen, is collecting data. You have to collect your data. And that data could be in a SQL database, it could be in CSV, Excel, in different types of sources. It could be in Aries, it could be in WellView, it could be, especially if you work for a small private company, or if you work for a smaller company, a lot of these small companies don't have a central data hub or a central data repository where all that data is stored, In that case, collecting that data becomes much more challenging, right? But if your company has a very good data warehouse where all your data is stored, then collecting that data would be much easier as opposed to not having a data warehouse. So collecting data is probably one of the most time-consuming piece of any machine learning project. And the fact of the matter is, you have to collect the data, you have to understand what you're trying to do, and you have to analyze the data, and that takes some time. So right now, 80% of the time is spent collecting data, and 20% of the time is spent, doing machine learning on that data. But we're trying to get to a point that you spend less than 5% of your time collecting that data, because everything is in a data warehouse, everything is in a central place, and you just go in and grab it, and that makes the process go much smoother and actually much faster. So in step one, collecting data is a very important piece, and after you collect that data, step two becomes cleaning that data. And cleaning that data, it basically means, you have to go and visualize the data. And to kind of explain these, like the first two steps, let's go to the next slide and then come back to this slide again. So if I go to the next slide, cleaning that data means you have to visualize the data. I have to understand, what kind of distribution plots I have. Do some, just plot some box plots, scatter plots to understand my data, to understand what am I trying to analyze and understand. And especially with distribution plots, it gives you a sense of, the distribution of each parameter. If you're trying to understand the relationship between, cluster spacing or sand per foot or well spacing to your production performance, you have to understand the distribution of that parameter. Because if you don't understand the distribution of the parameter, then it's going to be very hard to kind of come up with conclusive decisions at the end. So distribution plots, visualizing the data is super important. And that's number one. Before doing any kind of analysis, you import your data, you have to visualize your data to understand what you have, to understand the distribution, to understand your outliers, to understand which features are heavily collinear, And once you visualize your data, you can also see very clearly that you have, some anomalous points here and there. What do I do, with those anomalous points? Are these anomalous points actually true, or are these just, typos, and they would have to be removed? When validity of these anomalous points are in questions, well, then simply remove those anomalous points. So and you can see it like right away. If I do a simple scatter plot, just a cross plot of, let's just say, sand per foot versus EUR, and I have a sand per foot of 10,000 pound per foot. Well, have I ever tested a sand per foot of 10,000 pound per foot? Well, if you haven't tested that, then probably there's something going on with the validity of that data. So you really want to make sure that those anomalous points, those outlier points, get removed prior to deploying any type of machine learning to train a machine learning model. And then the next step is collinearity removal. So Collinear removal is actually a very simple thing to do and is highly recommended, especially for parameters that are heavily collinear. For example, based on your domain expertise, you understand that sand per foot and water per foot are most likely going to be heavily collinear, because the more sand that you pump, usually the more water that you would pump with that, right? So if you plot these parameters and you see a Pearson correlation coefficient of, let's just say, 90, plus 95%, then you have to remove one of the parameters. If the Pearson correlation coefficient is let's just say not as high as 0.9, then you can just keep those parameters. But if the Pearson correlation coefficient says that these two parameters are heavily collinear, then definitely consider removing one of the parameters, because they both provide the same information. So you're just introducing more noise into the model that is not necessary. So collinearity removal is a very important thing to do. And you can also apply dimensionality reduction. You can apply different techniques such as PCA, principal component analysis, and kind of reduce the dimensionality of your data. If you have multiple geologic features and all those geologic features provide you the same information, well, how about we do some type of dimensionality reduction to reduce that many geologic features to just a few geologic features that are interpretable and you understand heavily, and you can either do it by just simple calculations, or you can use some type of dimensionality reduction technique. And those techniques, they all have some advantages and disadvantages, including principal component analysis, which is heavily used. So I would be very careful, as far as how you treat that data, and just make sure that whatever technique that you use, you understand the underlying meaning of that parameter. So, for example, if you use principal component analysis, you might lose some of the interpretive capability of principal component analysis of that reduced dimensionality, and you just have to make sure if that's acceptable to you or not. So now we talked about data visualization, talked about anomalous detection, finding the outlier points. We talked about removing collinear parameters. Then you also do feature ranking and selection. Now, feature selection is probably one of the most important process in machine learning. Now, what I mean by feature selection is which features are you going to choose to include in your model. Do you choose, for example, why would you choose cluster spacing? Why would you choose well spacing? Why would you choose gas in place, oil in place? Well, all of these features that you choose would have to have some type of a direct impact on your output feature, which in this case, if you define your output feature as EUR per 1,000 feet, those features would have to have some type of an impact. So that's where domain expertise come in. So feature selection is simply heavily dependent on your domain expertise. And the more you understand the underlying problem, the more experience that you have in the industry, the more you'll be able to solve the problems. Unfortunately, a lot of the machine learning models fail, not just in the oil and gas industry, in different industries. And the reason for that failure is just lack of domain expertise. The best way to tackle a machine learning project is to combine data scientists and domain experts in that field. Combine those two together, and that's really the recipe to success. If you just hire a PhD student or a PhD guy, with no experience in that industry, and that PhD guy, could be a brilliant guy, but without any experience, it's very hard to really perform meaningful machine learning work. But if you combine that PhD candidate, which have who has a lot of experience in statistics and mathematics and everything else, with somebody who has domain expertise. That is the recipe to success in applying machine learning to different problems. So feature ranking and feature selection is another piece. And when I say feature ranking, you rank your features. You can use different algorithms such as random forest, which we'll talk about, to kind of rank the features to see which features fall at the bottom. And the features that have the lowest impact will fall at the bottom. You might consider removing those features, because if you remove those features, the impact on your model will not be as much, or will be negligible. Then finally, you can normalize and standardize your data set, and we'll talk about the equations in a minute. By normalizing, I'm referring to normalizing your data to be between 0 and 1, and by standardizing, I'm talking about standardizing the data, each column of your data to have a mean of 0 and a standard deviation of 1. So normalization, standardization is another important piece. And the reason for that is, let's just say you're trying to understand the relationship between sand per foot, water per foot, and so on and so forth on the production performance. If you do not normalize your data, well, let's just say if you just include sand per foot with a range of 1,000 pound per foot to 4,000 pound per foot, and then you also use cluster spacing, which has a range of 10 foot to, let's just say, 100 feet. If you don't normalize those data to be on the same scale, then you're not treating the problem on an apples-to-apples basis. So that's why it's very important to normalize or standardize your data depending on different algorithms. Some algorithms work much better with standardization, and other algorithms work much better with normalization. So now that we understand the essential action items in steps 1, 2, and 3, let's go back to this figure. So we're done with step 1, 2, and 3. We've done the normalization, standardization. Step 4 is to train the database based on various algorithms. And in this step, I think it is very important to understand which algorithm you're going to choose for the problem. Now, there are, as you saw, there are many different algorithms, and the type of algorithm that you choose depends on the type of problem that you're trying to solve. So some of these problems, like what is the size of your training sample, what kind of accuracy would you like to achieve, how much time do you have for training the model, how many parameters do you have, number of features that you have, just your training size sample. All of these would have a direct impact on the type of machine learning algorithm that you're going to choose to solve your problem. And also there's a very important concept in machine learning called bias and variance. Bias is simply referred to as the inability for a machine learning algorithm to capture the relationship, and that's called bias. And basically, you have to understand the relationship between bias and variance in a machine learning project. So the ideal machine learning model, a trained machine learning model, would have a low bias and low variance, which just means that when you train your model, you could do a very good job training your model. And then when you apply that trained model to test samples, it would also do a very good job. So if, for example, your training accuracy was, let's just say 95%, then you apply that trained model to a test sample that the model has never seen before, and your training and your testing accuracy is, close to 95%. That means you've done a very good job having a model that has low bias and low variance. So always remember, you want a model that has a low bias and low variance. And the way you do this is called cross-validation, where you split your data between your training and testing. Usually 70 to 80% of the data set is used for training, and then 20 to 30% of the data used for testing. So now what happens if you train a model and you have, let's just say, 95% training accuracy, then you apply that model to a test data set, and your testing accuracy is 50%. Well, that's a big problem. It just means that your model is overfitted. It means that what you've done with your model is you have memorized the trends as opposed to understanding and building a general model that would really that is going to help you predict stuff. So that's why it is very important to split your data to a training set and a testing set. And usually, as I said, it depends on the type of problem. 70 to 80% of the data is used for training, and then 20 to 30% of the data is used for testing. Train the model, look at the accuracy of that model, and then apply it to the test data set just to make sure the testing accuracy remains high as well. And if that's the case, that means you have a model that has a low bias and low variance, and that's the ideal type of machine learning model that you want to develop, right? And if your training comes out to be very high and your testing comes out to be very low, then you'd have to go back and understand what's causing that. Do you have to add more features? Do you have to fine-tune the parameters within each machine learning algorithm to optimize those parameters, and so on and so forth? So step number 4 and 5, make sure you do a cross-validation. You have the training set, you have the testing set, and then once you have your testing set, I would do one final check, and I would apply this trained model and deploy it real time, if you can deploy it like real time, to make sure that when you deploy it to a data set that the model has never ever seen before, it still holds up, and once you're happy with that blind set, then you move on and basically apply the model and use the algorithm. You can either there are two different type of machine learning projects. So some projects where you just build a model, you're just trying to understand the independent impact of each variable on the output feature. And the second type of model is where you develop a model and then you want to deploy that model real time. And in those cases, you would have to use some type of some type of technique to actually deploy the model real time to kind of send signals to the field real time. And there are a lot of companies that do that. So the steps are pretty easy. Steps number 1, 2, and 3. These are basically cleaning, collecting, and analyzing your data, making sure your data is normalized and standardized. You understand, the distribution plots and everything else. Step number 4 is when you train your model and choose and basically choose an algorithm that fits your model the best. And those algorithms, as I said, depends on the size of the training set, the accuracy, training time, number of parameters, number of features, and so many other parameters. And basically, once you're done with that step, then you go into the next step, which is cross-validation. You split your data into training and testing. You do a 70% 70-30 training test split. And then once you're done with that step, then I would do one final check and apply it to one more set of blind sets, which the model has never seen before. And if that still comes up to be with a high accuracy, then you go on and apply the model real time, or you simply just do a sensitivity analysis to understand the impact of each variable on the output feature if you're solving a problem using a supervised machine learning algorithm. And the reference for this is highlighted at the bottom. So we talked about this slide here. Now let's talk about the example that we solved. So we added a machine learning in hydraulic fracturing unconventional book that was on the second edition, and this is all coming from that book. And you can see basically this is just showing a scatter plot on the left hand side on different variables versus one another to kind of find anomalous points. If you see any anomalous points, you can find it like right away. This was all done in Python. We used the scikit-learn library. Like in this case, this was used. We used the Seaborn visualization library in Python. This heat map was also created in Python using the Seaborn library. All the machine learning analysis that we've done that I'm going to show you was used using the scikit-learn library in Python. So this is basically the heat map on the right hand side. This is the Pearson correlation coefficient, which is simply the covariance of variable x and y divided by standard deviation of variable x times standard deviation of variable y. And this Pearson correlation basically tells you which features are heavily collinear, so you can remove those features from the analysis. So if you see a feature that has Pearson correlation coefficient of 0.9, then I would consider definitely dropping that feature from the analysis, because that feature will provide you the same information. So that's how we basically determine which features to drop and which features not to include in our model. So this is the left hand side is used for anomaly detection, and the right hand side is used for collinearity detection and removal. So now let's also talk about feature normalization and standardization, how you calculate feature normalization. So as I said, depending on the type of algorithm that you're going to use, and some algorithm you are recommended to use, for example, standardization, and some algorithms such as ANN, you are recommended to use normalization. So the calculation is actually very simple. You just take each variable minus the min of that column or of that variable divided by max minus min of that variable, and that's how you normalize that feature in your data set. And then feature standardization is simply you take each variable and then each sample minus the mean of the data set of that feature divided by the standard deviation of the data set of that feature. So one is x minus min of x divided by max of x minus min of x, and the other one is x minus mean divided by standard deviation. And that's how you do feature normalization and standardization. As I said, depending on the type of algorithm that you're going to choose, some will use feature normalization and some will use feature standardization. The next thing is, as I said, feature ranking. So let's talk about which features have the most important impact on my model. There are different types of algorithms that you can use for feature ranking. One of the algorithms is called random forest, and random forest is basically a combination of ensemble of decision trees. Okay, and basically the way that random forest ranks the parameters is based on the parameters with the least important impact fall at the bottom of the tree. And those parameters can basically either be removed from the analysis or just not included in the analysis. Again, this is from the case study that we did from the hydraulic fracturing book on the second edition, and you can see in this case study, cluster spacing and gas content and proppant per foot had the highest impact on the production performance, which was EUR per 1,000 feet. So that gives you some understanding into your data that really what drives your performance. What is driving your production performance, which is very important. Is it your cluster spacing? Is it your proppant per foot? Is it your well spacing? And every field, every data set, every basin is different. And once you understand what drives your production performance, then you can hone in on those parameters and try to optimize those parameters. One of the things that I see all the time is that people try to optimize parameters that have little impact on the production performance. Parameters they for example play around with let's just say parameter X, and when you look at parameter X on this chart here, it might be at the very bottom of the chart. Well, if the importance of that parameter is 0.5% or 0.2%, why would you not ignore that parameter and focus on the parameters, such as, for example, in this case, this is just a synthetic data set, cluster spacing or prop per foot, things that you can control and change those parameters. Why would people focus on parameters that are not important? Well, that comes from lack of understanding from the data. Well, your data set tells you that the most important feature in this synthetically generated data set is cluster spacing. Now, why would you go and play around with shot density if the importance of that parameter is only less than 2%, whereas the importance of cluster spacing on the production performance is over 18%? I think the answer to that question just lies in lack of understanding the data and really understanding, doing these types of analysis to feature rank the parameters to understand what is it that really drives your production performance, and hone in on those parameters to optimize your production performance. So that's a very important slide that really shows you it gives you a feature ranking, and it shows you the importance of using some type of a machine learning algorithm to rank your features from high importance to low importance. Next thing, we applied two different, we applied many different models, and I'm just going to cover a couple, and then I'm going to show you the result of using support vector machine. I'm going to show you the result of using ANN, and I'm not showing the result of support vector machine in this case, but it was very similar to ANN. So support vector machine is basically a powerful supervised machine learning algorithm, okay? And the idea in support vector machine is to maximize the margin through a separating hyperplane. And I can explain this in this picture. So if you look at this picture right here, you can see, let's just say you have like just a cross plot of X and Y, and then you have your features here, and you have your let's just say this is a classification problem, and you have two features here. The idea in support vector machine is you're trying to draw a hyperplane. In this case, this solid black line is the separating hyperplane, in a manner that would maximize the distance between these points, these support vectors, closest to this separating hyperplane from here to here, and it would also maximize the distance from here to down here. So you're trying to maximize the difference between the red support vectors that are closest to this black line and the green support vectors that are closest to this black line. And this line can be drawn in a different way. You can draw this in this way, or you can draw it this way. There are different ways of drawing this separating hyperplane, but you want to draw it in a manner that the distance from here to here and from these support vectors to the separating hyperplane are maximized. And the reason it's called support vectors is because these points here that are closest to the separating hyperplane, these are called support vectors. So that's the idea in a support vector machine type of algorithm, which is a supervised machine learning model, which is a supervised machine learning algorithm. Now let's talk about ANN, or artificial neural network. So ANN, you guys have probably heard that a lot. ANN is a powerful supervised machine learning algorithm. And the idea of ANN comes from brain neurons, which acts as an artificial version of human nervous system. So basically, The best way to explain the neural network is to look at this figure on the right hand side, okay? And as opposed to support vector machine where you're trying to maximize the margin, in A&N you're trying to minimize a cost function. And that cost function is simply the difference between your actual values and your predicted values. This equation can be used as the cost function. Or sometimes if you look at Python, you can call it the loss function, But let's look at this figure. So in this case, I have my gas in place, I have my water per foot, I have my sand per foot, I have my cluster spacing, all of these features that I have chosen to be included in this model as my input features, okay? And then I have one hidden layer here. And in A&N, you could have multiple hidden layers. You could have 1, 2, depending on the complexity of your problem. The more complex your problem is, the more hidden layers and hidden neurons you're going to use. And I will try to focus on optimizing the hidden neurons first before moving on to adding more hidden layers. But different industries are different. I believe that a lot of the problems in the oil and gas industry can be solved with one hidden layer and optimizing the number of neurons. But if you work for a different industry, if you work for Facebook or somebody else that have terabytes of data and you're trying to build a machine learning model based on that, then you might have to use a much more complex type of A&N structure to optimize your model. So you have your input layer, which is here on the left-hand side. The middle layer, you have your hidden layer here. And each hidden layer, you have number of neurons. So in this case, you have 1, 2, 3, 4, 5, and so on and so forth on the number of hidden neurons. And then you're trying to tie all of this to the output feature or the output layer, which in this case is EUR per 1,000 feet. Your output layer could be, you could have multiple output layers, and in this case you just have EUR per 1,000 feet, but you could have Cube 30 per foot, Cube 60 per foot, Cube 90 per foot, and so on and so forth. So the idea behind this is you're gonna, each of these neurons that you see has a weight and bias, and you're basically changing the weight biases of these neurons until this cost function is minimized. So let's just say I have a weight of x1, weight of x2, x3, and so on and so forth on these hidden neurons, and I'm going to predict my EUR per 1,000 foot to be 2.5, and I'm going to look at the actual value of my EUR per 1,000 foot, and the actual value is actually 2.2, where I'm going to go back and adjust the weights and biases of these neurons, and then keep iterating on that model through those epochs, through those iterations, until the cost function is minimized, which means the difference between my actual and predicted values are basically minimized. So it's a very simple, actually, even though if you have heard of A&N, it might sound too complex and too sophisticated, but it's actually, the concept is very simple, and it's really not that difficult once you understand the underlying concept behind it. So just remember, the idea in an A&N model, like many other machine learning models, is to minimize the cost function. But the idea in a support vector machine model, which is just a different type of machine learning algorithm, is to maximize a margin, and that margin is basically to maximize the difference between those support vectors that I showed you versus that separating hyperplane. So now let's just say I've built a machine learning model. I'm happy with my training accuracy. I'm happy with my testing accuracy. I feel pretty good about it. The next step before you actually do a sensitivity analysis is to do grid search. Now, what in the world is grid search? Well, grid search is the process of applying various combinations of different fine-tuning parameters. So for example, in the A&N model, you have different fine-tuning parameters, such as what type of solver do I want to use to solve the problem? Do I use stochastic gradient descent? Do I use atom solver? Do I use, what type of solver do I use to solve the problem? You also have different types of functions. Do I use, tangential or logistic functions to solve the problem? And how many neurons am I going to use to solve the problem? Am I going to use 50 neurons, 20 neurons, 30 neurons, 1,000 neurons, 1,000,000 neurons? How many neurons would I choose to solve the problem? Well, that's so you can see that there are so many different fine-tuning parameters within, for example, just the A&N that can be adjusted, and that would have, an impact on your model. So what do I do? So I would run grid search, and grid search basically runs different combinations of different fine-tuning parameters. And basically, to make it simple for you, for those of you that are actually coders, it's basically a nested for loop. I'm going to do run this model with this many, let's just say with 20 neurons, but use stochastic gradient descent solver and use let's just say logistic function. Then I'm going to run it with 25 neurons with the same solver and logistic function. And then you use 30 neurons and so on and so forth. So once I'm done with the number of neurons, and I can move on and just say now change it from stochastic gradient descent to atom solver and try different combinations of different parameters. So it's basically a nested for loop that I'm trying to solve. And there's actually a library in Python called grid search that you can use. So for that library, you can run it, depending on how many fine-tuning parameters and the range of those fine-tuning parameters. It can run for, hours or days or even months. In the past, I've tried applying grid search to some problems that had really so many different fine-tuning parameters, and also the data set was huge, so it really took weeks for that grid search to get optimized. So that's when the time comes in. How much time do you have to do the project, and really what are you trying to achieve, and is the 90% answer better than 99% answer or 100% answer? So that's when the importance of grid search comes in. Always make sure to apply grid search to make sure that your model is optimized, and then once you're happy with it, you can also visualize, applying that final model obtained from grid search and visualizing your loss function and your iteration to make sure that as the number of iterations goes up, your loss function goes down, and in other words, your model, your cost function is being minimized for the A&N model. And then also, once you're done with it, look at your model prediction and look at your test set and see if you're happy with it. Look at your R-squared to see if your test R-square is high enough for you to trust the model to go to the next step. And in this case, the next step is to do a sensitivity analysis. So now I'm trying to understand what is the impact on, so I've trained a model now, right? Now I can understand what is the qualitative and quantitative impact of each parameter independently on the production performance. In this case, I've applied it to cume gas per foot. I've also applied it to EUR per foot. The trends are similar, and you can see, for example, if I go from, let's just say, 1,200 pound per foot of sand to 2,000 pound per foot of sand, what is the quantitative impact on cume gas per foot going from here to here? And that's very important, because once I understand that, then I can run economic analysis to see, well, if I go from this design to this design, really, am I getting much higher productivity to pay off to pay off the additional capex that I'm incurring? And same thing with cluster spacing. What is the qualitative and quantitative impact of cluster spacing on my, for example, O&Gas per foot. Again, these numbers, guys, are just synthetically generated database that we created for this book that we published for the second edition. So in this case, this is just for illustration purpose. But just remember that once you have your own data set and you understand what is the qualitative and quantitative impact of each parameter on production performance, that's when the value of machine learning comes in. That's when the value of sensitivity analysis comes in. So in this case, I'm just showing you just a couple of examples on the sensitivity analysis that we did to understand the qualitative and quantitative impact. Hope this made sense. In conclusions, I'd like to say machine learning is a powerful subset of AI to decipher information and pattern from complex data. Data preparation, domain expertise are two of the main drivers behind a successful machine learning implementation. Just make sure you combine the domain expertise with statistical knowledge. You have the guys that are that have the statistical and mathematical background for a successful implementation of a machine learning model. And then qualitative and quantitative analysis can provide significant insight on the impact of each parameter independently on the production performance. Once you train a model, you can do sensitivity analysis on anything and understand the impact of each parameter on the production performance independently, as opposed to, oh, we changed this, and that. We changed so many variables at a time, so we can't understand what is the impact of that parameter independently. That's where the power of machine learning comes in, that you can understand, even though if you had so many changes in your design, you can understand the impact of each parameter independently. So with that being said, thank you so much for listening. If you have any questions, let me know. I'm on LinkedIn. Just add me on LinkedIn, and hope you enjoyed it, and looking forward to your feedback.